Uh, Hi everyone. Am I live? Hi. Hi. Um, Hi everyone. So the usual round of questions. Am I audible and am I visible? We'll wait for some time to make sure that it's live. Okay. Thank you, Anushka. Um, Hi. Okay. So it's clear. So should I start my session? Yeah. Okay. Hi. So, for this long chapters of Intro to ML, the initiative by DSC and NSEC, today's session is about probability and statistics. So, before we even went live, there were a lot of comments about how probability is a bit confusing and how it has not really gone inside most of our heads. It is truly. I started probability as a subject, as a fourth subject when I was in class 11 and 12. And when I started, it was pretty confusing, but slowly kind of held a grasp to it. And here I am with my knowledge about it. Um, Without further ado, I'll share my screen so that you can see my slides. Yeah, so once my slides are visible, could you please just inform that to me in the live chat section? Yeah, yeah. Hopefully it is. So the topic for the day: probability theory and statistics. Yeah, exactly. People ignore probability in their high school only to later realize how much important it is in ML. Uh, I didn't really take up probability with a much thinking about what I would do in the future. I just took it as a fourth subject because I really loved maths, and it really came on use when I started my journey with machine learning. So, hi, this is Rajwrita Nath. I am basically here because I love maths, and there is no further introduction I would want of myself right now in this slides. And without further ado, because it's already been 9 minutes and there's no point talking about me when we can just talk about probability and statistics. So, the very first part of the topic that it is today is probability theory. Yeah. What exactly is probability theory? First of all, it is the fundamental of machine learning, if not a total fundamental, definitely one of the key topics in machine learning. A grasp of probability and statistics in general is very important if anyone wants to excel in this subject. Probability theory is nothing but a mathematical framework. It is used for quantifying our uncertainty about the world. It will allow you, as well as the software you create, to reason effectively in situations where being certain is quite impossible. Yeah, where being certain is quite impossible. So it has been at the foundation of many machine learning algorithms, which we have already covered in the past, quite a few of them. And most of the cases, we've realized how much it is important to calculate, say, simple values like mean, median, when we have blank values. Those sessions have been covered. But again, a quick recap of that. So it is the foundation of many machine learning algorithms, and the entire goal of this session is to get you accustomed with some basic philosophy of probability and statistics. So let's discuss some perspective regarding this topic. Okay. So what exactly is probability? We know the term itself defines a lot of it for us. So most people know that probability of an event is some value between 0 and 1, cannot definitely be negative, as say suppose you can't really say that the probability that head is going to occur at a toss of a coin is negative. It's something, a value between 0 and 1. It indicates how likely my said event is going to occur, and seems simple enough and actually is quite simple. So if we talk about perspective here, there are two perspectives to it. One is the objectivist perspective and the other one is the subjectivist perspective. So the objective perspective is that this randomness is quite fundamental to the universe itself. Now, if I would say that the probability of a fair coin coming up in, say, suppose heads is 0.5, it's because that is what the nature of fair coins dictates. Now, alternatively, if I talk about, say, the subjectivist point of view, it is nothing but probability is nothing but it represents our degree of belief that a particular event is going to occur. Say, suppose if we know the initial position of the coin and how much of the force was applied to it, then we could easily determine with certainty if it would come up as heads or tails. Now, under this perspective, it is simply a measure, probability is a measure of our ignorance, like not knowing certain parameters, like, say, suppose the force which we are applying to the coin. Now, this quote quite definitely concludes my subjectivist approach to probability. God does not play dice with the universe. Yes. Now, before we go into any topic, there are some axioms and some vocabulary which are essential in any study. So, we will also similarly discuss a few of it. Probability, as I had already said, is the possibility of various outcomes, right? So the set of all possible outcomes is called the sample space. Like when you are rolling a die, you have possibilities of getting a 1 or a 2 or likewise till 6 at the topmost face of the die, right? So if I put these in curly brackets, 1, 2, comma, till up to 6, then that forms my sample space. And similarly, say if I say in case of a coin toss, then that becomes heads or tails. So that is my sample space. And the two basic axioms of probability that we say are that the probability of a said event to occur is anything between 0 and 1, both inclusive, because as I said, it cannot really be negative, and and the summation of all the probabilities for the occurrence of each individual member of a set sample space will sum up to get me 1. Another important vocabulary term which comes a lot in anything which is related to probability and statistics is definitely random variable. As the name suggests, a random variable x is simply a variable, takes up random values, and hence the name. Now, we often indicate a specific value x and we take it on with italics. Say, for example, if I say that x in my given problem represents the outcome of a coin flip, then we might discuss a specific outcome as x is equal to heads. And in this case, x is my random variable, and x is equal to heads is one such value which this random variable can take. Now, random variables can be broadly classified into two types. One is the discrete random variable and the other one is the continuous random variable. The discrete random variable, again, as the name suggests, takes up discrete values, say the head or tail, like that, and continuous random variable if, say, the age of a person, or maybe not age, sorry, the weight of a person. It can be 50, 50.5, not really restricted to integer values. And coming to discrete and random variables, it is very important to ascertain the fact that we understand which type of random variable we are dealing with in our said problem. Otherwise, a proper probability distribution cannot really be attached to those variables. So, yeah. So, with that, as discussed with discrete random variables, we have some discrete distributions. Till now, is there any problem or any issues regarding the sound or the slides? Um, can I get something in the live chat if possible, maybe? Okay, so I'll proceed. Okay, thank you. Okay, cool. So, as said before, say suppose the random variable I am discussing about in the first stage is some discrete random variable. So we need to attach a distribution which caters to this discrete random variables. And in that regard, we have a few discrete distributions, say the uniform distribution, the binomial, and the Poisson distribution. So the very first distribution is my uniform distribution. This distribution occurs when the different values of the random variable are equally probable. Like, for an instance, and I am pretty sure I'll be taking the example of a die or a coin multiple number of times simply because it makes understanding easier. At least that's what it did for me. But I'm pretty sure the more you study about these distributions and probability in general, you will have examples in real and daily life which you can attach with any one of these, and it will make your understanding of probability even clearer. So suppose, for instance, we have an unbiased die is and we're rolling that die, and the random variable that we have x, we have denoted it as x. This random variable denotes to the number of points on the uppermost face of the die. Then in this case, my random variable x will have a uniform distribution. That is number one, and that is the most important part. Now it takes the values 1, 2, and then so on and so forth till 6, and each of them has the probability of 1 by 6. As said, uniform distribution specifically caters to those random variables which are equally probable. So, yeah, this die example is one clear example which will give you a proper insight into this problem. Now, in general, the distribution is defined by the probability mass function. Probability mass function gives you a function which relates the random variables to a said function, and in this case, my function is fx is equal to 1 by n, and that is for x taking up a plus h, a plus 2h. Your a and h are fixed real numbers, and n is a fixed positive integer. We can see that h to h is because these random variables that these value points in my sample space are equally spaced. Like the difference between 2 and 1 is the same as the difference between 6 and 1. So if all these parameters are checked, then we can fit a uniform distribution for our discrete random variables. Now, with my uniform distribution, we can calculate the mean, the variance, skewness, the kurtosis, and things like that. But that will go into deeper topics of uniform distribution, and the entire objective of today's session is to give a brief overview of probability and statistics, something that people learn forever, to sum it up, or at least try to sum it up in an hour. So the next distribution is binomial distribution. Just a second. Okay, yeah. So before we go into what exactly binomial distribution is, it's very important that we discuss what repeated trials signify, or to be put simply, what exactly is a trial? Okay, anyone, we've all studied statistics some way or the other in the past years. Any idea about what exactly is a trial? You may put it in the live chat, and maybe we can have a small insight and discussion into what it is. Like, what do you understand by the word trial? And the best thing about probability, or say, suppose statistics in general, is that the terms that are there, they kind of give out what they actually mean in some way or the other. So most of the times when I missed some chapter in statistics or probability in my exams, I used to try to figure it out from the terms that are given. A cheap way of passing in exams, but sometimes did help. So any idea about what is a trial? Hmm, okay, set of possible outcomes, maybe single performance of well-defined exam experiments, as far as I remember. Yeah, all close. Experiment. Yeah. So by the word trial, what we mean is an attempt. It's an attempt to produce a particular event which is, say, neither certain nor is it impossible. By chance or anything random. Okay. Okay. So yeah, like say throwing a die to get a six is a trial. Now we can repeat that event. Now we are not exactly certain that in my next throw another six is going to come, and neither the occurrence of six in my next trial is an impossible event. So as I said, neither certain nor impossible. Trials are said to be independent in relation to any event if the probability of the event in any trial is not affected by the supplementary information about the results of any other number of trials. That is, in this case, say my next event is no way related to what I just experimented right now. Say when I'm rolling a die for the second time, it does not matter if it came as a 1, 2, or even odd, whatever number has come before that. It's not dependent. My second experiment is not. So the key point in trial is that it has to be independent, and the outcome of a trial is neither certain nor impossible. And with these three criteria is defined the word trial. Now, a series of trials is said to be a Bernoulli series of trials. Why and when is it done so? If, say, the possible results of any trial can be divided into two classes, which we conveniently call success and failure. The trials are independent, and the probability of success remains constant from trial to trial. Again, a short example: when n throws of a fair die may be looked upon as a set of Bernoulli trials, where appearance of a 6 on the uppermost face may be taken as a success with probability 1 by 6 in each trial, and n tosses of an unbiased coin, say, will give you a set of Bernoulli trials once again, which will give you the outcome of, say, if I define it as if I'm getting head, then it will be regarded as a success with probability half in each trial. And similarly, my failure in this experiment is to get a tail in the coin, and that will be regarded as a failure, and the probability is half again. My success and my failures are complementary to 1. That is, if my success is x probability, then my failure is going to be 1 by my 1 minus x. Yeah. So with these two terms here, we have the binomial distribution. It deals with Bernoulli series of trials. The distributions which can be fit into this is, yeah, exactly. So I understand, yeah, the formula. Yeah. So yeah, that is what it is. They're like pretty easy terms which are just summarized into this video so that it's a quick overview and a quick revision maybe. So yeah, my PMF is fx is equal to, oh, again, PMF is probability mass function. It's a function which is defined to the discrete random variables. So in this case, it is NCX, or we choose x from n values, and then p to the power x, q to the power n minus x. Here p is my success ratio and my q is failure. So as discussed earlier, q is nothing but 1 minus p. So this distribution is known as Bernoulli's distribution, and when n is equal to 1. Here the random variable x is the number of successes in a set of n. Bernoulli trials, p is the success, and np, they are the parameters. Like when we discuss further into binomial distribution, we'll later know that in this case, np will give me my mean, and any complex formula of any distribution has some logic to it. I would love to specify the logic behind this. So if we have to derive this distribution, we can proceed as follows. Say the probability of getting x successes and n minus x failures in any specified order in a series of n Bernoulli trials. So with p as the probability of success in a trial, we have it as p. It can occur x times, right? So p to the power x. Okay, yeah, Rishiraj, what is x is equal to 0 bracket 1 n? It is a common way of denoting 0, comma 1, comma 2, dot, 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 till n values. Here my spacing between each value is 1, and it's a way we denote this in case of statistics and probability generally. So yeah, that is what it is. Again, so p can occur, that is my success. I'm defining it as it can occur as, say, suppose x times in my total distribution of n number of sample space values, and my failure will occur n minus x. So p to the power x and q to the power n minus x. Now these successes can be placed among these n gaps in ncx number of ways. So if we multiply all of it, then voila, we have my function, which is my pmx function in case of a binomial distribution, which is ncx, p to the power x, and q to the power n minus x. Going on to the next one, we have the Poisson distribution. Till then, Rishraj, is your question clear? Like, is my answer clear, or should I like go about it once again? Okay. So meanwhile, while anyone asks anything or confirms, I'm gonna go forward with it. Yeah. So my next distribution, which is the Poisson distribution, is another probability distribution which deals with discrete random variables. But the important thing here is, in this case, the random variable can assume a countably infinite number of values. Yep, makes sense. Yeah, Rishira, thank you. So it can assume a countably infinite number of values. The distribution is again defined by a function which is e to the power minus p to the power x, and x factorial. Here p, or in some cases it is denoted by lambda even, is the parameter of the distribution, and it is usually seen that function of x will be greater than equal to 0. It's a basic property again, which we had described in the beginning slides. Yeah. The unique thing about Poisson distribution and the way we understand that all of it kind of is interconnected and interlinked is we can regard a Poisson distribution as a limiting form of a set distribution. So any guesses as to what is the set distribution? It is a distribution which is covered previously and a part of a discrete. So that's basically two options. Makes it easy. But any answers? Hmm, okay, I'll wait for some, because if I continue, it will literally just give out the answer. In this case, the distribution that I am referring to, if I increase my number of trials to limit tends to infinity, then probability of success giving out more information here in a trial tends to 0. But NP remains finite. Any guesses? Yeah, 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 Anushka, yeah. Thank you. It is binomial distribution. So yeah, Poisson is a binomial distributions limiting form. Here my number of trials tends to 0, and if I put the success close enough to 0, then my NP, which is my parameter in this case, will become finite. Yeah, there is a proof to it, but this is how it is. Like if you apply limit to my binomial function that has been described earlier, if I put my limit tends to infinity, it will give you the formula which is displayed right now on screen, e to the power minus p to the power x, and divided by x factorial. The only thing which I would like to mention is if you are deriving this limit problem, then my p in case of a binomial distribution is a separate parameter itself. It does not denote the success of an event as I have described. Like it, take it as maybe say suppose lambda in this case, so that there will not be a further confusion regarding it. Okay, so next we will go on to some of the continuous distributions. So at this point, can you give a real world example of a Poisson distribution? Yeah, sure. Okay. So if I say that the probability that an individual will suffer a bad reaction from a particular injection is 0.001. So you can see that the probability is quite small. Like the success probability here is quite small. And I have to determine the probability that out of 2000 individuals, more than two individuals will suffer this bad reaction. So in this case, what we see is my NP, that is 2000 into 0.001, will come up to something small and something finite, but the probability of calculation is made from 2000 individuals or 2000 samples. So that N kind of is a huge term. Uh, and see, we say that N tends to infinity. In reality, it does not really have to be something close to 2 lakhs. The most important thing of Poisson is that my NP, that is my parameter, should be something finite. So, yeah, Nidhin, is your example, does it really clear your doubt or should I give another one? Okay, so while Nidhin responds, yeah, thank you. So, the next set is some continuous distributions. Now my continuous distributions are rectangular and normal, but before we go further into this, I'm pretty sure at 10:33 or something, most of the mode of the people that are there right now in live. Okay, sorry for interrupting, but we have Akshay with us in this live. Seems pretty unreal. And thank you. He's the GDE in ML. We've met during Dev Fest, and from that time onwards, he's been a constant inspiration and a guide. Thank you for making it here, Akshay. I would fangirl for 10 more minutes right now, but I guess let us just, without further ado, here. Anyway, so this is probably the mood, as in the pictures, because probability is something that has been a huge topic, and yep, it is the ML wizard here. Yeah, that will be a lot of fangirling and fanboying if it is a term right now. Okay, so that is the mood of the day, maybe, or of the hour, maybe, but it's mostly because it's a huge topic. And as we said, machine learning requires perseverance, it requires dedication more than anything else, and every individual topic in it needs further study. This session or every session in the Intro to ML initiative of us is a way in which you understand what the different topics are and which are the places you need to lay stress onto and so on and so forth. So, some continuous distributions, there are two kinds here. One is the rectangular and the other one is no uniform. Yeah. So the rectangular, or we can also term it as the uniform distribution. Yes. Here, here the random variable x again has a rectangular distribution if it has a probability density function of the form fx is equal to 1. Okay, there is a slight problem. I'm so sorry. There'll be a 1 by b minus a. There's a division sign which is missing here, but yeah, that is it. And it is denoted in the diagram beside it. Yeah, so it deals with all values of x in between the two intervals of a and b, and it is 0 elsewhere. Again, quite evident from the graph itself. So again, fx is greater than 0, and if we integrate fx in minus infinity to plus infinity interval, then we will sum it up and get it up as 1. Yeah, kind of shut her up. Okay. So if it's perfect now, should I go ahead? Like a confirmation from people in the group, in the live chat, I mean. Yeah. So normal distribution, again, as the formula seems pretty complex, again, if you put it out into sums or when you start solving your algorithms with it, it becomes easier. Uh, it's a kind of like a bell-shaped graph. It's also known as the Gaussian graph. And in the further sessions that we are going to conduct, we will have more such descriptive analysis of this particular distribution. Yeah. So we've studied a lot about. Okay, that was a great time of me looking into the screen. Yeah, I would love to extend the session, and it would be great if I got the chance of doing so. And I don't think the time that I was not there has been of any waste because we've all got to interact with Akshay. It has been a delight. Okay, what is this happening? I am not really sure. Anurag Bhaiya, if you're there, could you share my screen where my face is not visible? It's okay. And then, okay, sorry for that embarrassing time lapse. But as soon as the slide is up, I'll start once again. What's all this got to do with machine learning? Okay, so as discussed, machine learning is an interdisciplinary field, right? It uses statistics, probability, algorithms to learn from the data and then further provide insights which can be further used to build intelligent applications. So, as we've discussed, okay, thank you. That's very sweet of you to not really care about your English exams that much. Thank you. Okay, so as discussed earlier in the previous sessions, we kind of have a brief idea about what supervised learning or unsupervised learning or reinforcement learning are actually defined as. So we will have this quick relation which we can derive between the various theories of probability and these branches of learning in machine learning, right? Yeah. So, okay, there is a certain glitch. I'll wait for it to go away. I'm sorry for the delay that is happening, but hopefully it is worth it. Yeah. So by the time the slide is coming up, supervised learning, yes. So in supervised learning, what actually happens is we have label data, and our goal, if we have to put it in a line, a sentence, then our goal is to learn from this label data, right? So again, if it is a jargon, and I don't really want this session to be one with jargons, so what exactly is label data? For some input X, we know the desired output. That is what label data is to be defined. Now, again, a classic example is identify what is an image. That can be a label data, right? So we can learn the mapping from X to Y in different ways. First, you could learn the probability of Y given X. I'm pretty sure someone was talking about Bayes theorem. Yes, that is an application here. So, yeah, that is to say a probability distribution over possible values of Y given that you're observed a new sample X. Yes. So machine learning algorithms that find this particular distribution are called discriminated. Now imagine I tell you that there is this individual who has long hair, has beautiful eyes, has say a height of 5'7", and so on and so forth. If I give you various parameters regarding that individual, you can guess what or who am I talking about, right? So in that case, it's nothing but a case of Bayes theorem. You're given the parameters in the form of x, and you have to determine what is the probability that it is a said person A, suppose. So that is a very simple case of probability of y given x, and it's being beautifully linked with machine learning, supervised learning to be specific. The next part after supervised learning is, as it's very guessable, is unsupervised learning. So unsupervised learning, it is a broad set of techniques. It's used for learning from unlabeled data. It's different from supervised, yes, obviously. The previous one uses labeled and this one uses unlabeled. We just have to use some examples, some samples X, but no output Y. Common unsupervised tasks include grouping similar data points together, a classic example of clustering. And those of you who have been in Nikita Gandhi's wonderful session that had been described very elaborately and way more beautifully in that session. So yeah, that is clustering. Now, characterizing the distribution of unlabeled data is useful for many tasks, right? So one example is anomaly detection. So if we learn probability of X, where X represents my normal bank transaction, say suppose, then we can use this probability to measure the likelihood of my future transactions. If we observe a transaction with low probability, we can flag it as a suspicious and a possibly fraudulent transaction, yes. So clustering is one of the canonical problems of unsupervised learning. Say I am giving you certain data points originating from separate groups. Now, how can we determine which group does each of these points belong to, right? So in this case, the method is to assume that each group is generated from a different probability distribution, suppose, and if I solve the problem then it becomes finding the most likely configuration of these distributions that I have sorted my various sample values into. The next one and the last branch in this case is the reinforcement learning. The field of reinforcement learning is all about training artificial agents to perform well at specific tasks. The agents learn by taking actions in their environment and observing reward signals. Send me the link for the forum. Yes, Akshay, it will be sent to you as soon as possible. Yeah, so the agents here learn by taking actions in their environment and observing reward signals based on their behavior. That is, if I have to sum up what reinforcement learning is in a crude way, that is what it is. Now, the goal of this said agent is to maximize its expected long-term reward. And in this case, again, probability is used in reinforcement learning for several aspects of the learning process. Now, it is very obvious or it's quite general that you may have picked up on the word expected in the goal. The agent's learning process often revolves around simply quantifying this uncertainty of the utility of taking one specific action over another. Characterizing the distribution of unlabeled data is useful for many tasks. Yeah. The next branch in our topic today was statistics. So statistics, like I said before, probability deals with predicting the likelihood of future events, right? Now, statistics comes in the play when it involves the analysis of the frequency of my past events. There are various ways in which we can divide statistics into parts, but the part that I'm going to discuss today is when I'm dividing descriptive statistics into two parts. One is univariate and bivariate. As I had said that statistics involves the analysis of the frequency of past events, and as we know, a picture speaks 1,000 words. So what better than branching descriptive statistics and understanding what actually is happening? Again, as we've seen, we've had cases where we have to make histograms as discussed in the previous sessions. So again, these are all parts, like everything when you move about in machine learning, you will need these small concepts in bits and pieces everywhere in your journey in ML. And here we are today at 10:56, all listening to this. So yeah. So different ways is one of them univariate and the other one bivariate. Uh, so univariate data includes central tendency, say mean, mode, median, and dispersion, range, variance, maximum, minimum, quartile, standard deviation, all of that. Like all of these are small terms and the plots that we use to visualize my univariate data are typically bar charts. They can be histograms, they can be pie charts, and so on and so forth. Bivariate, on the other hand, this bivariate analysis involves the analysis of two variables for the purpose of determining the empirical relationship between them. The various plots used to visualize bivariate data, as the name suggests, bi as in two. So that's two variables, right? So data which includes two variables, and if I have to plot that data so that it's better understandable to the person who's going through the process, it's through scatter plots, box plots, and so on and so forth. So the first one, which we would discuss now, is scatter plots. So scatter plots or a scatter diagram is a diagrammatic representation of bivariate data. Now suppose we are given n pairs of values of variables x and y, taking two mutually perpendicular straight lines as axis of reference for x and y. Each pair of given values can be plotted. So if I'm taking one as x, the other as y, and it's given a value of 1, 2, where say 1 is denoting my x parameter and 2 my y parameter, as simple as that. So in that case, we can form this set of axes and we can plot individual points on this given plane, which this axis are forming. Right. So for a scatter diagram, one can know the nature and the intensity of the association, if any. It might be a case of zero or no correlation. We'll be coming forth with that topic. But yeah, in case of zero correlation, there will not be any degree of association between the two values, right? So in that case, it will be zero. Okay. So it can be a positive correlation if my dots on the plane go upward. It can be a negative if it's going downward, and it will be just scattered with a haphazard pattern. There's no real correlation. Again, the term clearly mentions it for you. Then it's a zero. Okay, so correlation, again, don't really mean to make it a jargon because it's pretty simple. And I remember this questions of what is correlation coming up quite a few times in the previous sessions that have happened. It's very simple, and once you know about it, it's quite simple and will not take much of your brain space to analyze what it is. So by correlation, we mean, okay, I have to go. Thank you so much, Akshay, for being throughout in the session. It means so much to all of us, and I'm sure all of us love you here. Thank you so much. We'll talk to you later. Okay, so correlation, we mean the association of interdependence between two variables. If two variables be so related that a change in the magnitude of one of them is accompanied by a change in the magnitude of the other, then they are said to be correlated. So correlation may be linear, it might be non-linear. There just has to be some amount of link between the two values which are there in this bivariate data. So we shall restrict our discussion in this situation to correlation which is linear. Now, going further with it, if one variable is found to increase on the average as the other increases, then the variables are said to be positively correlated. Again, if one variable decreases on the average as the other increases, then we say that it is negatively correlated. A third situation may arise, which I was talking about earlier, whereas one variable increases, the other remains constant on the average. So in that case, zero correlation occurs, and the variables are said to be uncorrelated, to put it down into simple words. Now, in order to measure the coefficient of correlation, that is the degree of correlation. You can quickly Google what Pearson's coefficient of correlation is. It's simply a method by which you can get a quantitative approach to an idea that you're now forming, and all of it is used to do that. Yeah, some if I'm talking about some properties of it, it has to be a pure number, symmetric about x and y axis. But all of these terms are going to sound quite the form of jargon right now. But yeah, more and more as we go about it in the further sessions, or the more and more you study about it, it's going to be clearer. In this regard, we can also talk about regression, maybe a little bit of it. By regression of a variable y on another variable x, we mean the dependence of y on x on the average. So in bivariate analysis, one of the major problems is the prediction of the value of, yeah, that is the link. Yeah. So it is the prediction of the value of the dependent variable y when the value of the independent variable x is known to us. So the problem becomes simplified if we can express y as a mathematical function of x. Say suppose y is equal to h of x. So in that case, we have a mathematical function which relates both of these, and we can perform linear regression equations. We can form linear regression equations with the help of it. Um, So that is pretty much all from my side for today. It's been awesome staying here, connecting with people, learning as well as sharing all that I know. And I'm sorry better the next time. So with that, if thank you so much everyone for staying patient throughout it all. Thank you so much everyone. So yeah, surely I'll take loads of medicines, and sounds kind of dramatic, but this entire adrenaline rush about this session has kind of cured my fever. Yeah, so with that, we wrap it up. If there are any questions or if you want to connect with me apart from this, these are the few basic social media handles I'm available on. I'm also there on Twitter, Medium, Facebook, all of that. And anytime in the Telegram group of DSC and NSEC or the forum. And then, yeah.